All right, I want to talk a little bit about these kinematics problems that we're doing. And every single one of these part 2D kinematics problems is based on the following. We're going to have a situation, the situation we discussed in class is a table. A ball is launched at a horizontal speed, and what happens is that it lands on the ground. And what we did is we tackled this problem in two parts. We had an x part and a y part, and I'm going to write those down now. So in the x direction, we used d equals rt, and we set r equal to whatever v naught x was. And we solved for whatever we could solve for. And usually it didn't give us a complete answer. And what we had to do to end up finishing the problem was we had some initial height that we called 0, and then we landed on the ground, and we wanted to, and by the way, this distance d that I'm talking about is this horizontal distance right here from the edge of the table all the way out to where it lands. In the y direction, we write down three equations, one for the position, one for the velocity, and one that doesn't include time, just in case we need it. So here's the idea. We're going to fire a bullet, and ideally it should move horizontally and hit a target. And instead what happens, not ideally, it's aimed directly at the target. What happens is that because it's actually on Earth in a gravity field, it actually ends up curving like this. So here's our target. There's the bullseye. And then we've got the bullet here. Okay. And instead of hitting the target, it curves down. So here is what we're saying. This distance is 140 meters. We know that the rate is 280 meters per second. And in the y direction, what we know is we'll start our initial height is 0. Always do that, unless I tell you otherwise. This y is unknown, and that's what we want. They won't say it that way. I won't say, hey, find the missing y letter. It's gonna be deliberately something that you're expected to be able to read from the problem and figure out on the tests. Okay? So by how much will the bullet miss the target is the question. And we know that v naught in the y direction is 0. This is v naught in the x direction. It has nothing to do with the vertical. Vy vertical is unknown. The acceleration is gravity. And the time is also unknown. Unknown here as well. And remember, the time it spends traveling in the x is exactly the time it spends traveling in the y. So what we're going to do is first, we're going to break down the x equation, then we're going to break down the y. So here it goes. D equals RT, always open with that. 140 meters is 280 times the time that we're looking for. When we isolate, we're going to get t is exactly half a second. And so now I can use that value in the equations. And I want to get the height that it falls. I'm just going to grab my first equation. Y is 1/2 gt squared plus v naught y times t plus my initial height. Y is what I'm solving for, 1/2 times 10. Now the time it's spending traveling horizontally is exactly the time it's spending falling. So that's 0.5 squared plus 0 plus 0. So when I actually solve for y, when I simplify this out, I will end up getting that it falls 1.25 meters. Now let's be really clear. It says how fast would the bullet need to go in problem 3 to miss the target if it misses the target by only half the distance. Let's be really clear. We're not missing the target because we shot left or right. That's not what's going on. What we really, and let me say one other thing. When I say how fast does the bullet need to go, this is deliberate phrasing. It's not intending to be vague, but this is how physics problems are written. What we should really say is how I'm going to translate this into better language that might help a student. It doesn't necessarily get written this way. I'm going to try to be mindful of this on the test, but I can't guarantee this. What we should really say is this. How fast should the bullet's horizontal firing speed be so that it falls only half the distance below the target? That's really like how it should have been phrased. So I'm going to actually write this as better and clearer phrasing. Okay, when we have that in mind, I'm going to go with the same idea. Okay, so we're still 140 meters away. So D is RT. I'll still start with my X equation. This is not a fraction. This is just me labeling a column here to shove my X stuff into. So D equals RT. So I've still got 140 meters equals the rate times the time. Both of these are unknown. So now I move to the Y equations. In the Y direction, I can say Y is 1/2 gt squared plus V naught Y times T plus Y naught. I don't even know if I have enough information here in the Y. Let's see what we got. So I know Y naught is 0. I know Y is half the distance I got here, so that's going to be 0.63. Okay. So falls half the distance. I'm just going to say that's 1.25 divided by 2, which is 0.63. V naught Y is 0. Vy is unknown. Time is unknown. And we have the acceleration of g. So y equals 1/2 times 10 times t squared plus 0 plus 0. The y is 0.63 equals 10 t squared. And so we end 10 divided by 2t squared. So 0.63 divided by 5 is t. And that's going to be 0.126 under a square root is the time. And so when I actually isolate that particular time, let me just go ahead and do that now. The time will be, sorry, give me a sec, 0.63 divided by 5. I take the square root of that, and I end up getting 0.35 seconds. Now I can use that right here. So 140 equals R times 0.35. And when I actually isolate my rate, I end up getting about 394 or 395 meters per second. All right, so that's part 2 of the exam.